Imagine a tunnel. Not just any tunnel, but one that cuts through the very fabric of space and time. This is the essence of a wormhole, a theoretical concept that has captivated physicists and science fiction enthusiasts alike. Wormholes, also known as Einstein-Rosen bridges, are essentially shortcuts through space-time. Picture a piece of paper folded in half. Now imagine a tiny hole punched through both layers. That hole represents a wormhole, connecting two distant points in space, perhaps even different points in time. These cosmic shortcuts, if they exist, could potentially allow us to traverse vast distances, even journey to other universes, in the blink of an eye. But how do these mind-bending concepts arise from the realm of physics? It all began with Albert Einstein and his groundbreaking theory of general relativity. Einstein's equations suggested that massive objects could warp space-time, creating the potential for these fascinating shortcuts. Imagine space-time as a two-dimensional surface. When you fold this surface, distant points can come into contact, creating a bridge or tunnel between them. This is the basic idea behind a wormhole. However, the reality of creating or finding a wormhole is far more complex. Theoretical physicists have proposed various models, but none have been proven or observed in the real world. Some theories suggest that wormholes could be created by manipulating exotic matter with negative energy density, a concept that remains purely speculative at this point. If we could harness such technology, the implications for space travel would be revolutionary. Imagine traveling to distant galaxies or even parallel universes in a matter of moments. The mathematics behind wormholes is intricate and challenging, involving complex equations and theoretical constructs that push the boundaries of our understanding. Yet, the allure of wormholes continues to inspire scientists and dreamers alike, driving us to explore the mysteries of the universe and the possibilities that lie beyond our current grasp. Einstein's theory of general relativity, published in 1915, revolutionized our understanding of gravity. This groundbreaking theory was a departure from Newton's classical mechanics, which had dominated scientific thought for centuries. Einstein proposed that gravity is not a force pulling objects together, but rather a curvature of space-time itself, caused by the presence of mass and energy. It describes gravity not as a force, but as a curvature of space-time caused by mass and energy. This was a radical shift in perspective, suggesting that massive objects like stars and planets bend the very fabric of the universe, creating what we perceive as gravitational attraction. Imagine a bowling ball placed on a trampoline causing it to sag. This simple analogy helps us visualize how massive objects distort space-time. The greater the mass, the deeper the sag, and the stronger the gravitational pull experienced by objects nearby. Similarly, massive objects like stars and planets warp the fabric of space-time, influencing the motion of objects around them. This warping effect is what keeps planets in orbit around stars and governs the motion of galaxies across the cosmos. In 1935, Einstein, along with physicist Nathan Rosen, further explored the implications of general relativity and stumbled upon a fascinating possibility: wormholes. These theoretical passages through space-time could potentially connect distant regions of the universe, offering a shortcut through the vast cosmic distances. They were studying black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape. Black holes represent the ultimate warping of space-time, where the curvature becomes so extreme that it forms a singularity, a point of infinite density. Their equations suggested that a black hole could be connected to another region of space-time by a tunnel-like structure, which they called an Einstein-Rosen bridge. This concept was revolutionary, proposing that space-time could be folded in such a way that two distant points could be directly connected. This hypothetical bridge, later known as a wormhole, offered a tantalizing glimpse into the potential for shortcuts through the cosmos. While still purely theoretical, the idea of wormholes has captured the imagination of scientists and science fiction enthusiasts alike, inspiring countless stories and further research into the mysteries of our universe. Wormholes have become a staple of science fiction, often depicted as portals for interstellar travel and time travel. From the cosmic wormhole in the movie Interstellar to the time-traveling DeLorean in Back to the Future, these fictional portrayals have captured the public's imagination and fueled our fascination with the possibilities of wormholes. In these stories, wormholes serve as gateways to distant stars, allowing characters to traverse the vast expanse of space in an instant. They also often serve as conduits for time travel, allowing characters to journey to the past or future. While these depictions are often based on scientific concepts, they often take creative liberties, blurring the line between science fact and fiction. While wormholes are theoretically possible within the framework of Einstein's general relativity, their existence remains purely hypothetical. Scientists have yet to observe any direct evidence of wormholes, and many challenges and unanswered questions surround their formation and stability. One major challenge is the need for exotic matter, a hypothetical type of matter with negative mass and energy density. This exotic matter is theoretically required to keep a wormhole open and prevent it from collapsing under its own gravity. However, the existence of exotic matter itself remains unproven. Despite these challenges, the possibility of wormholes continues to intrigue physicists, and research continues to explore their theoretical properties and potential implications. Section 5. A Journey Through Time. The Potential of Wormhole Travel. If wormholes do exist and are traversable, they could potentially unlock the secrets of time travel. By creating a shortcut through space-time, a wormhole could, in theory, allow us to travel to different points in time, both past and future. Imagine entering one end of a wormhole and emerging at a point in time before you even entered. This mind-boggling concept, while theoretically possible, raises numerous paradoxes and challenges to our understanding of causality and the nature of time itself. Section 6. The Paradox of Time Travel. Untangling the Challenges. The possibility of time travel through wormholes raises a plethora of paradoxes that have puzzled philosophers and physicists alike. One classic example is the grandfather paradox, which asks what would happen if you traveled back in time and accidentally killed your own grandfather. Would you cease to exist? If so, how could you have traveled back in time in the first place? These paradoxes highlight the potential for contradictions and inconsistencies if time travel were possible. Section 7. The Quest for Exotic Matter. A key ingredient for wormholes. One of the biggest hurdles in the quest to understand and potentially harness wormholes is the requirement for exotic matter. This hypothetical type of matter, characterized by negative mass and energy density, is theoretically necessary to keep a wormhole open and prevent it from collapsing under its own gravity. Exotic matter, if it exists, would behave in ways that defy our everyday experience. Instead of being pulled towards a massive object by gravity, it would be repelled. This bizarre property is crucial for stabilizing a wormhole, as it would counteract the immense gravitational forces that would otherwise cause it to collapse. Section 8. Peering into the Unknown. Current Research and Future Directions. While wormholes remain firmly in the realm of theoretical physics, scientists continue to explore their properties and implications. Researchers are investigating the mathematical framework of wormholes, searching for potential observational signatures that could hint at their existence. Some scientists are exploring the possibility of creating microscopic wormholes in the laboratory using powerful particle accelerators. While these experiments are still in their early stages, they offer a glimmer of hope for gaining a deeper understanding of these elusive cosmic shortcuts. Section 9. Conclusion. Wormholes. A portal to the cosmos and beyond. Wormholes, those hypothetical tunnels through space-time, continue to captivate our imaginations. They are often depicted in science fiction as shortcuts through the universe, allowing for faster-than-light travel and instant connections between distant points in space. These fascinating constructs push the boundaries of our scientific understanding, challenging us to think beyond the conventional limits of physics. While their existence remains unproven, the theoretical possibility of wormholes opens up a Pandora's box of questions about the nature of space, time, and the universe itself. Could they be used for time travel? Might they connect parallel universes? These are questions that intrigue both scientists and the general public alike. As we continue to explore the cosmos and delve deeper into the mysteries of the universe, the quest to understand wormholes will undoubtedly lead us to new discoveries. Each step forward in our understanding of these enigmatic structures could revolutionize our grasp of the cosmos and challenge our fundamental assumptions about the nature of reality. The study of wormholes forces us to confront the very fabric of space-time and the limits of our current scientific paradigms. Whether wormholes remain a theoretical curiosity or one day become a reality, their exploration will continue to inspire us to reach for the stars and beyond. The dream of traversing these cosmic tunnels fuels our imagination and drives our quest for knowledge, pushing humanity to explore the farthest reaches of the universe.